This is section 5.3. Welcome to chapter 5. In this chapter, we'll be investigating systems of differential equations. That is, there will only be one independent variable, but there will be multiple dependent variables. And all of our equations will, of course, involve not only these dependent variables, but some of their derivatives as well. That is, there'll be differential equations. Here I've given a few examples of what such systems could look like. In this first example, we have x1 prime equals 2x1 minus 3x2. Just to clarify how we would interpret this, the independent variable is actually not stated anywhere in this differential equation. But as has been customary in this course, we interpret that independent variable to be t. So I believe the way I would interpret this is x1 and x2 are two dependent variables. x1 prime is of course the derivative of the dependent variable x1, and the independent variable for both of those is t. In addition to this first equation, which gives me some relationship between these dependent variables and one of the derivatives, I have a second similar equation. In this second example, I have very similar ingredients. This time it looks like it's a second order differential equation because I've got a second derivative here. In this third example, I do have a function with just t's in it. So this is a function of just the independent variable. And I once again have dependent variables x1 and x2, and the two equations that comprise my system involve both those dependent variables along with some of their derivatives. In this case, again, they're just first derivatives. And then in this third example, I have three dependent variables, x1, x2, x3. I again assume that the independent variable is t, and then my equations give me relationships between the dependent variables and the derivatives of those dependent variables. So in each case, the value of the derivative somehow depends not only on the value of the function itself, or the value of the dependent variable itself, but it also depends on the value of other dependent variables. And it's exactly that type of relationship that systems of differential equations are designed to capture. Such systems are prevalent in a wide range of models covering a pretty wide variety of physical contexts. One classic context, one that our textbook author relies on pretty extensively, is a population modeling context in which we're interested in modeling the growth of two species. So each species is represented by its own distinct dependent variable, with the independent variable being time. And I've briefly outlined here how we could build and interpret such a model. We'll actually return to this model repeatedly throughout this chapter, so I won't go into too much detail here. And I'll also just mention briefly that another way we could find ourselves dealing with a system of differential equations would be to extend a mass spring system, like we've discussed in recent chapters, by adding a second spring and a second mass. So we would attach a spring to the original mass, then another mass is attached to that second spring, and this could of course be extended to involve any number of masses and springs, eventually leading to a pretty complicated system. For now, it suffices to say that such a quote-unquote machine, if you will, would be modeled using a system of differential equations. This section, actually the first few sections of this chapter, aren't designed to give a too detailed look at differential equation models just yet. It's hopefully intuitively clear that the main mathematical methodologies we'll need to use to deal with systems of differential equations will borrow pretty directly from tools required to deal with systems of algebraic linear equations. Things like substitution, elimination, matrix representation, matrix tools, etc. So the purpose of the first three sections of this chapter are to review those tools. And actually, I've chosen not to work through all the details of the most preliminary tools and techniques from this area of solving systems of linear equations. This area is called linear algebra. So the first two sections in this chapter, 5.1 and 5.2, review the most fundamental ideas about solving systems of linear equations. What I've chosen to do is briefly summarize some of those ideas at the beginning of this lecture. We'll get to that in just a sec. Then to go ahead and move into the main topic of this section, which is a slightly more advanced linear algebra topic, namely eigenvectors and eigenvalues. If you feel you need more review of the preliminary topics I'm just summarizing here, I definitely encourage you to look at sections 5.1 and 5.2 in our textbook in detail. The author provides lots of good detailed examples in those sections. So on this second page in the notes, I start describing some, quote, facts about solutions of systems of linear equations. Again, these are ideas and techniques that I hope you have some familiarity with. In fact, as I pointed out above, we have solved such systems of linear equations several times throughout this semester while doing various steps required to solve differential equations. Think about when you needed to solve for the coefficients in y sub p when doing the method of undetermined coefficients, or the method of variation of parameters centered around solving a system of equations. So hopefully these facts are familiar to you, but if you do want a more detailed explanation of these facts again, you should take a look at sections 5.1 and 5.2 in the textbook. But what I've laid out here are what I think are the most essential facts about systems of linear equations. I have basically 4 big bullets, and these facts aren't directly related to differential equations. They're general facts about systems of linear equations, but they'll be fundamental when we do eventually start using these techniques to solve systems of differential equations. So the first fact is extremely fundamental, and it states that for all algebraic systems of linear equations, there are 3 and only 3 types of solutions possible. I call these types of solutions because they're sort of different categories of the solutions to the system. The first is that the system could have a unique solution. Remember that the solution to a system is a set of variable values that make all of the equations in the system simultaneously true. So in this category, in this case, it could be that there is exactly a unique set of variable values that satisfies that restriction. It could also be true that there are infinitely many sets of variable values that satisfy that restriction. That is to say, there are infinitely many solutions to the system. The third possibility is that there are no solutions to the system. That is, it is impossible to find a set of variable values which will make all of the equations true simultaneously. That's it. There are only those 3 possible types. So for example, if you have a system of linear equations, it's impossible for that system to have exactly 2 solutions. Either you're going to have exactly 1 solution, or you're going to have infinitely many solutions. It would be impossible to have exactly 2 distinct, 2 and only 2 solutions to the system. So the fact that these are all 3 of the possibilities is very, very important. In the next bullet, I state and demonstrate just sort of a notational convention. So I say here that algebraic systems of linear equations can be conveniently represented using matrix and vector notation. And these notations are crucial because they enable us to do abstract calculations instead of always dealing with some specific system of linear equations. And just to demonstrate briefly how these notations work, here's a specific system of linear equations, and this representation is usually the preliminary representation of such a system that we encounter. There's nothing necessarily wrong with it. We just want to introduce an alternative notation utilizing matrices and vectors, which allows us to represent such a system a little bit more concisely. And here's how we do that. We define a few ingredients. First of all, we have a 2 by 1 matrix, that is 2 rows and 1 column, that holds the variables. So I call that the vector x, and this is how I'll write that vector. x1 in the first row, x2 in the second row. Then I define a matrix which I've called capital M here, which contains the coefficients in my original system. If If you look at my system, the coefficients in the first equation are 1 and -2. Those are the coefficients on the variables. So those become the entries in the first row of this coefficient matrix. Similarly, my coefficients in my second equation are -3 and -1. Therefore, the entries in the second row are -3 and -1. And then the last ingredient, the last thing that I haven't accounted for here, is this kind of right-hand side. And so I put those into a vector as well. That's also got 2 rows and 1 column. Then I can actually rewrite this exact same system in a much more concise way using this matrix and vector representation. And if you remember how matrix multiplication works, if you were to perform this matrix multiplication and then set entries in the first row equal to each other, you would regain this exact first equation. Similarly with the second row and the second equation. So as I said, the real benefit of this notation is that it allows us to perform operations in an abstract way without dealing with a specific coefficient matrix, for example. So to that end, we will usually call this coefficient matrix M, capital M. And then this vector on the right-hand side we'll often call the vector B. So this system has the structure M times the vector X equals the vector B. And this is a very, very concise representation of every system of linear equations. So we'll use this notation extensively. And then sometimes we can make this notation even more concise when the variables are sort of obvious. We don't bother writing those. And so then we generate what's called an augmented matrix. So this will be one single matrix. On the left-hand side, I'll write my coefficient matrix M, and then I'll write sort of a tall vertical line that separates that coefficient matrix from the right-hand side vector B. And then I'll refer to this as an augmented matrix. The last 2 bullets, the last 2 important facts that I want to mention here quickly, have to do with something called the determinant of a square matrix. The adjective square here indicates that I've got the same number of rows as columns in my matrix. And if I have such a matrix, I can define a numerical value called the determinant. And the determinant is kind of a helpful tool because it indicates several important properties about the matrix in a real concise way. So how do I calculate the determinant? Well, the determinant of a 2 by 2 matrix, so suppose I have sort of a generic 2 by 2 matrix, I've labeled the entries simply A, B, C, and D, then the determinant of that matrix, which I'll write this way here, determinant of M, or sometimes I'll write with tall vertical bars, they almost look like absolute value bars around my matrix. And if I just have the 2 by 2 case, then I simply multiply along this diagonal. So I have A times D, and then I subtract the product along the opposite diagonal. And that little formula there is true for every 2 by 2 matrix. So anytime I have a 2 by 2 matrix, which is kind of the smallest interesting square matrix, then to calculate its determinant, I'll always follow that procedure. Multiply along this diagonal minus the product along this diagonal. How about larger matrices? Well, as I've stated here, there are several methods for computing determinants of larger matrices. I have kind of my preferred method, which is called Cofactor Expansion, and I've chosen to hold off on explaining that here, and I'll demonstrate that through some upcoming examples. And then this last bullet, this last fact that I wanted to discuss briefly right now, demonstrates one way in which the determinant of a matrix can yield properties about that matrix. Specifically, the determinant of a matrix, of a coefficient matrix M, can be used to indicate which of those 3 cases we're in regarding the type of solutions that my system Mx equals B has. Recall from a second ago that we stated that there are only 3 types of solutions. We could either have a unique solution, infinitely many solutions, or no solutions. So in this, for example, that we provided here, that would be true. There's either a unique solution to this system, or infinitely many solutions, or no solution. And as it turns out, we can identify which of those cases we're in based on the value of the determinant of the coefficient matrix. And that's what I'm trying to show or explain in this last bullet. It says that if the determinant of the coefficient matrix is non-zero, then the system mx equals b has a unique solution for all b vectors. That is to say, if my determinant of the coefficient part, just the m, is not zero, then whatever I put on the right-hand side of that system of equations, the resulting overall system will always have a unique solution. If instead the determinant equals 0, we've got a couple possibilities. If the determinant of my coefficient matrix equals 0, and I choose to have a right-hand side of 0. Maybe I don't choose it, but maybe the particular system that I'm interested in has all zeros on the right-hand side. We actually call such a system homogeneous, which is a term we've used previously in this course, and in a certain way, the meaning is the same as to how we've used it previously. But anyways, if I happen to have a system where the right-hand side is all zeros, and I calculate the determinant of the coefficient matrix, and the determinant ends up equaling 0, then that means that this system has infinitely many solutions. This bullet here is actually really crucial to what we want to accomplish in 5.3 when discussing eigenvectors and eigenvalues. So let me just restate it one more time. If we have a system where my right-hand side equals 0 and the determinant of the coefficient matrix equals 0, then the overall system will have infinitely many solutions. What happens if I have a 0 determinant but the right-hand side is not all zeros? Well, in that case, it kind of depends on my choice of b. There's going to be some choices for which the system has no solutions, but then for other b vectors, so for other values on the right-hand side of the system, there will be cases where the system has infinitely many solutions. So this bullet here is a little bit more ambiguous because it's impossible to predict exactly what type of solutions we'll have unless we know the specific right-hand side in our system. So in those 4 bullets, I've very briefly summarized what I take to be the key ideas from sections 5.1 and 5.2 in chapter 5. And what I would like to do is next work through some examples that highlight these 4 ideas. But if you feel like you need more explanation regarding any of these ideas, as I've said, please check out section 5.1 and 5.2 in the textbook. So let's go ahead and take a look at an example. Here I have a pretty friendly little 2x2 system. There's 2 variables, x1 and x2, and 2 equations that hopefully will enable me to solve for those 2 variables. If our objective was to simply solve this system, I could use either of the traditional techniques of substitution or elimination to work through to the solution. Here, let me demonstrate that briefly. Here I've used elimination to solve the system. I simply add my 2 equations. You'll notice that these 2 coefficients on x2 are lined up perfectly to cancel each other out when I add the 2 equations. And I quickly conclude that x1 equals 7/2, and then substituting that into my first equation, I'm able to quickly identify that x2 equals 5/2. So I notice that there is a unique solution to this system because there is exactly one set of variable values. x1 equals this, x2 equals this. There's exactly one set of variable values which make both of my equations true simultaneously. And again, if my goal was to simply identify the solution to this system, I'd be done. But I want to use this example to demonstrate a few of the other properties that we discussed just a moment ago. So first, let me highlight the matrix and vector representation of this system. So here I have explicitly spelled out the 3 ingredients that build this system. I have my coefficient matrix, which I create by simply grabbing the coefficients on the variables in an orderly way. My variable vector is just a simple 2x1 vector that catches the 2 variables that are at play in this system. And then my right-hand side vector is this vector b, which is the values that are not coefficients on the variables. These are like the constant values on the right-hand side of my equations. So as was mentioned above, I can represent this system using these matrix and vector ingredients. And if I wanted to be even more concise, we can use what's called an augmented matrix to represent this system, where I have left out, in a sense, the variable vector because I understand what that variable vector is by the context, and have simply written the distinctive ingredients in this system, the coefficient matrix along with the right-hand side vector. And then to distinguish between those two components or ingredients, I draw this tall vertical line. And then it is common to do the calculations required for solving this system in the context of this augmented matrix. Let me demonstrate that. Here I perform what are called elementary row operations, by which I can replace an existing row with some sum of the current rows. In this case here, I want row 2 to be replaced by the negative of row 1 plus row 2. So I take in each entry the negative of the row 1 entry, and I add it to the current row 2 entry, and that becomes the new row 2 entry. This procedure is called row reduction, or sometimes called Gaussian elimination. It has quite a few names actually, but I'm effectively performing all of the operations that I would perform using another technique such as elimination, but I'm doing them all in this matrix format. And in this particular case, the system is small enough that using traditional elimination techniques wouldn't be too difficult, but as systems get larger, this matrix representation is significantly more efficient. And then I'll just point out that if I look at this final form, this is called the reduced row echelon form, or the RREF of my original augmented matrix. In this form, I recall that these values represent the coefficients on x1 and x2, and then this augmented line in a sense represents an equal sign. And so if I rewrite what this first row is telling me in terms of variables instead of in this matrix form, it tells me that 1 times x1 plus 0 times x2 equals 7 halves. That is to say, x1 equals 7 halves. Similarly, this second equation says 0x1 plus 1 times x2 equals 5 halves. So I get the exact same solution that I derived earlier using the elimination method. The one last detail I'd like to highlight in this example is regarding the determinant. In this case, my coefficient matrix is square, and so I can calculate its determinant. Here's the notation for that. I would say the determinant of M, or I would write the matrix itself, but instead of writing parentheses, which I'm accustomed to writing around my matrix, I would write these tall vertical bars. And then to perform the actual determinant calculation, remember I simply multiply these two entries along this diagonal, and then I subtract off the product of the entries along the other diagonal. Simplifying, in this case, gives me 2. What's significant here is that this determinant is not 0. And if you refer back to the last bullet above, that indicates that using this coefficient matrix, I will always get a unique solution for the system mx equals b, and that will be true no matter what this right-hand side vector b is. In our particular example, b was 1, 6, and based on 2 methods of calculation, we did in fact get a unique solution. But what this non-zero determinant is telling me is that that result was no accident. I could choose any b in the world, fill this vector with any 2 entries, and in every case you will always get a unique solution. And we know that's true because the determinant of the coefficient part is equal to some non-zero value. All right, we kind of covered a lot of ground with that example. Let's take a look at another example and try to point out some of these same sorts of details. In example 2, we once again have a 2 by 2 system. There are 2 variables and 2 equations. Let me actually take sort of the reverse process. from the previous example, let me start by looking at the coefficient matrix M, and let me quickly calculate the determinant of this coefficient matrix. So since it's a 2 by 2, I apply my standard formula. I multiply along this diagonal, 2 times 1 minus the product along this diagonal, and in this particular case, that determinant does equal 0. And referring to the last bullet above, if I get a 0 determinant, that indicates that there are two possibilities. I could have infinitely many solutions to this system, or this system could be inconsistent. There could be no solutions. That is to say, it is impossible for this system to have a unique solution. Well, which of these two cases is actually true for this particular system? That depends on the choice of this B vector. In this particular case, we have the vector 1, 3. Let's go ahead and work through the steps necessary to solve this system, and that will indicate which of these two cases we're in. So I've once again used the matrix technique, and I've done the operations required to solve this system in the context of this augmented matrix. I won't explain those steps, but hopefully those all make sense. And then I've gotten to a point where if I was to unmatrixify, that is, if I was to take this matrix version and rewrite the standard equation version, I get something like this. And from the first row, I see that negative x1 plus 1 times x2 should equal 3. It's pretty uninteresting. But in the second row, I'm told that 0x1 plus 0x2, that is 0, needs to equal 7. This is, of course, a contradiction. When this happens to me, the first thing I do is I double check all my calculations to make sure I haven't made a mistake somewhere. I think I've done everything correctly, and so this contradiction actually indicates that the original system has no solutions. So based on the 0 value of the determinant, we knew that that was one of the possibilities. We could have ended up with either infinitely many solutions or no solutions, and it appears that using this particular choice of the vector b, my system will end up having no solution. So just to demonstrate the other possibility, let me consider a different system. Specifically, let me consider this system where I've just got zeros on the right-hand side. As I mentioned, in linear algebra, we refer to this system as a homogeneous system. And this is not the same system of equations that I started with. This is a different set of equations because now my first equation says 2x1 minus 2x2 equals 0, as opposed to my original equation, which said I should have 1 on the right-hand side. So this is a different system. But looking at the last bullet from above, that bullet indicates that this system, where I have 0 on the right-hand side, should always yield infinitely many solutions. Here's how that plays out. If I was to repeat the same operations that I used previously when modifying this matrix above, I claim that the coefficient part of the matrix would still turn into this, but the B vector would remain 0. If these two entries are both initially 0, then all of the allowable operations that I could potentially perform to the matrix will not change the value of either of these zeros. So I claim that if I was to repeat these exact steps, this is the reduced version of the matrix that I would end up with. Now when I unmatrixify, the second equation, which previously was a contradiction, is now true. And so since that is not a contradiction, that indicates that I'm not in the same situation where I have no solutions. What I need to do next then is use the first equation to identify some relationship between the variables that are at play here. It's easy to see that this first equation is telling me that x1 has to equal x2. So one way to think of that is that the solution to this system can be built by choosing any value for x2 that you want, and then you just make sure that x1 has that same value. One way to represent that is to say that my solution vector x is equal to x2 in the first component, x2 in the second component. I could actually, these are each just some number, so I could factor that out and I could rewrite it this way. So we do in fact see that this system now has infinitely many solutions, because for any choice of x2, if If I multiply that by this vector 1, 1, then that resulting vector will be a solution to this system. Just as a case in point, if I use x2 to be 3, then the vector 3, 3 will be a solution to this system. Or if I pick x2 to be negative 17, then the vector negative 17, negative 17 is a solution to this system. So there are infinitely many choices of vectors or pairs of values which simultaneously make both of these equations true. And as I mentioned already, I could predict that that would be the case because the coefficient matrix has a zero determinant. And just to reiterate that if my coefficient matrix has a zero determinant, then when I'm trying to solve a system which has a zero right-hand side, I'm guaranteed that that system will have infinitely many solutions. Alright, these two examples were pretty brief, but hopefully they have refreshed some details about systems of linear equations and or introduced a couple new ideas. And as I've said a couple times, if you want more details about the concepts covered in these first two examples, please take a careful look at sections 5.1 and 5.2 in the textbook. What I'd like to do next is to go ahead and move on to the topic of this section 5.3, which is something called Eigenvectors and Eigenvalues.